Okay, hello and welcome class. So this is design of steel structures and I'm engineer Ranjan R. Garmi. So today we are going to discuss about the block shear. So let us define first what is block shear. So it is actually a phenomenon of failure on a certain connection configurations where the block of material at the edge can tear out. So this is the effect of the concentration of our axial forces on the bolts. Of course, there will be a stress near the connection of the bolt to that of the member or the plate. Say for example, let us have a tensile member here subjected to a force P, and of course we should note that this member is connected through a rivet or a bolt to a gusset plate. So this is what we call the shear block. So in that manner, so that shear block will tend to tear out. Hence, if we isolate the free body diagram of that one, we will have two stresses on that block, namely the shear and the tension. So the tension comes with an area BC, while that the shear, we have this portion. So this portion, the total length times the thickness is the block shear. While on the tension, this length BC times the thickness is its area in tension. So remember that the block shear might occur on the gusset plate or on the tension member itself. So when we have the gusset plate here, all we have to remember is to determine the edge of that gusset plate. So that edge along the direction of our force is noted, so that we just have to project that edge up to the half of the bolt at the far end. So this is the block shear for the gusset plate. So block shear might also occur in your tension member. By the way, this shaded portion here, D, E, F, G, is the block shear for the gusset plate. So our concern here is that this length plus this length, of course that length is the net length wherein we have deducted the space occupied by the bolt, okay, as well as the upper portion. Remember that the shear block area is parallel to the direction of your axial force, while that perpendicular section, say this line DF, less the half of diameter of 2 bolts, is a tensile area. So again, we have the shear area, just the length of these red lines multiplied by the thickness, and then the tensile area perpendicular to the force P. And this is the area. Of course, that is a net length DF, subtracting the 2/2 dimensions of our diameter. So in the same manner, your tensile member would also be subjected to the block shear. So again, we concentrate ourselves on the tensile member. And on the tensile member, we'll just have to note the edge of that tensile member. The edge of the tensile member is the start of our block shear. So, meaning that is the starting point of the tearing, like on the gusset plate a while ago. So this is the area, the block shear. And then the shaded portion here will be the block shear HIJK on the member. So likewise, the length parallel multiplied by the thickness parallel to the axial force is our shear area. Once again, the far end here is the tensile area. So the tensile area, again, is the net area. Of course, from the gross length of I to K, we deduct the half of the diameter of the 2 bolts. So we can now determine the equation. Rn here is the nominal strength. Normally, we can also express this in terms of T or tensile capacity. So the concept is the nominal strength is equal to the strength from your shear stress plus the strength derived from the tensile stress, because as mentioned, there will be two stresses, the shear stresses and the tensile stress. Hence, we can expand the equation, and your RV, or the strength derived from the shear, accounts only for 60%, of course. So 60%, and that strength from the shear is associated with the fracture. Remember, in dealing with fracture, we deal with FU. Of course, with the net area. So A and V is the short for the net area from the shear. We add the effect of the tensile stress. So the tensile stress, of course, we also use the fracture because block shear is always associated with fracture. This time, our multiplier to the second term is the net area due to tension. And again, I would like to repeat that the net area due to tension is the perpendicular area to that of the axial load. So this expression is applied for uniform configuration. When we say uniform configuration, there is no staggered connection. For non-uniform configuration, or an arrangement where there will be a pitch and a gauge distance, we have the equation, the nominal strength is also the sum of the strength from the shear and strength from the tension. Hence, we expand the equation. We have the same expression for the first term, only that on the second term we'll just have to multiply the second term by 0.5 of the half of it. So this is the effect of the staggered connection. Now you will notice that on the first term, this is actually an expression for rupture. So we take note from the previous lessons or sessions, we have a comparison between the yielding and the fracture. So when we have a yielding, we deal with Fy. And if we have a fracture, we deal with Fu. So there will be an upper limit in calculation of the strength nominal, and that is actually expressing your first term by the yielding. So notice that the first term here includes Fy, and the area multiplied to this Fy is the gross area from the shear. So when we say gross area, we do not actually deduct the space occupied by the hole. So likewise, for non-uniform configuration, there will be an upper limit equation, Rn, Fy, gross area from the shear, plus Fu, net area from the tension. Of course, we always pair that with 0.5 for the second term. So that is the difference. You just have to multiply 0.5 to the second term for non-uniform configuration. So with this concept, the equation will be simplified to a certain factor UBS. So UBS will be used now to distinguish the uniform configuration and non-uniform configuration. So from that, we can now have the equation Rn is equal to 0.6 A and V plus Fu A and P, and the upper limit equation, you'll just have to change or deal with Fy for the first term and the gross area. Of course, this is the upper limit. So between the two equations, it should be always that this equation should be less than this equation. Hence, between those equations, we can choose whichever is the lowest among those two. So now to distinguish uniform configuration and to that of non-uniform configuration, you just have to insert here the factor UBS, okay, wherein UBS for uniform configuration is 1, and for non-uniform configuration, that is 0.5. Now this equation is actually intended for English units. So what will be the difference to that of the SI units? So in here, we use the same equation, only that we just have to change the factor 0.6 to 0.3. Okay, and this will be for SI units. Let us have this problem. Compute the block shear strength of the tension member in figure. The holes are for 7/8" diameter bolts, and A36 steel is being used. So we take note of the strength for yielding and for fracture. So this is the illustration wherein notice that we have a uniform configuration. first things first, of course, just like what we did a while ago, we need to establish the far end edge of this tensile member. Now, for considering the net tension, say NT, we'll just have to project a length here, okay, the length up to the edge of the bolt. So this is the area of the tension that we have discussed a while ago. Of course, this line shall start with the far end edge of the tensile member. So computing A and T, the net tension, this is equal to, of course, this is the thickness, okay? Just have to multiply the thickness times that length. And that length is actually 1.5 or 1.5. Now we less the diameter of our bolt. That's 1/8. Of course, that is only half of the diameter. Now, recall that we always add 1/8 to that of the diameter of the bolts to get the net area occupied by the bolt. So we only consider half of this bolt. So therefore, the net area will be equal to 0.375 square inches. Moving on to the net shear, of course, this is the edge, and then the shear extend up to the last bolt. So this length times the thickness is the net shear area. The net shear area here is equal to, of course, first the thickness, and then that length. Total length is covering 3 plus 3 plus 1.5, or that is 7.5. Then from that, of course, we need to deduct the holes. Okay, so the effective area for the holes is 7/8 plus 1/8, just the same. And there are 2.5 bolts because the bolt on the right far end is only half, and we need to deduct 2 from the mid portion. So 2.5, or there are 2.5 bolts included in this configuration. So this is the half of that bolt we are talking about. And these are the 2 bolts. So 2 plus 0.5, that is 2.5. Then from that, you can now compute the net shear area to be equal to 1.875 square inches. So in here, we also need to consider gross shear GV. Why? Because, as discussed a while ago, we need to have an expression for the first term of the upper limit of our Rn, or the tensile capacity. So the gross shear area will be equal to, of course, the 3/8 times 7.5. So notice that we do not deduct any holes. So that is barely the length times the thickness. So that will be equal to 2.813 square inches. Now for our equation, of course, we need to insert UBS here. In this configuration, it is a uniform configuration in a sense that there is no staggered connection. So applying that equation now, the nominal strength for the first term, we have 0.6 times 58 times 1.875, the net shear area, then plus, so our multiplier is 1 since we have a uniform configuration, so 58 is our FU, and the net tension area is 0.375, and that will yield to 87 kips. So moving on to our upper limit, of course, we use the same equation. So by the way, in here, we should note that the equation, first term is 0.6 Fy AGV plus Fu ANT. And 0.6 here shall be banished into the equation for the first term. Okay, once again, we have dealt with Fy AGV for the first term. And of course, there will be factor UBS here, just the same. Hence, we just apply this equation. So Fy is 36 KSI. The gross shear area is 2.813. So here we have a uniform configuration for a factor of UBS 1 times 58 FU and the net shear area of 0.375. So we come up with a value of 82.51 kips. Now between the two, of course, we should choose which is lesser. So knowing that Rn is equal to 82.51 kips, we have to apply LRFD. Of course, recall that phi for fracture is 0.75. Hence, we have this equation. Phi Rn is 75 of 82.51 or the Rn. Hence, we have the design load equal to 61.9 kips. By allowable strength design, we have omega is 2.0 for fracture, and the allowable strength is just the quotient of Rn to that of the omega. So applying that formula, we have allowable strength 41.3 kips. So moving on to the next problem. So in here we have an angular section 100 mm by 75 mm by 6.25 millimeters. So it is connected by 19 millimeter diameter rivets, assuming A36 steel where Fy is 248 megapascal and Fu 400 megapascal. So the assumption here is that the diameter of hole should be 3 millimeters larger than the rivet diameter. So therefore, 19 plus 3 is 22. 22 millimeter is the effective length occupied by that rivet. So here is the illustration, the angle. So we have the given dimensions, okay, and the thickness of 6.25 millimeter. So on the other view, on the top view, we have the spacing 75 millimeter on the top element of the angle, wherein this is staggeredly spaced on the top bolt. Okay, of course, the half of 75 is 37.5 millimeters. So our task is to determine the tensile capacity basing on the yielding of gross area. Letter B, determine the capacity of the section based on the tensile fracture of the net area. And letter C, determine the capacity of the section based on the block shear failure. So of course, we want this to be straightened. The first is to compute for the gauge distance, since we have here a staggered connection, wherein if we are going to straighten that top fiber of this angle or the top leg, you have to compute for our gauge distance. Now this is the gauge distance. Of course, we are familiar with this formula. G1 plus G2 minus the thickness. So the gauge distance is equal to, of course, from the edge to the center of the bolt on the top leg is 43.75. On the other leg or the lower leg, we have 62.5. Of course, we deduct the thickness, 6.25. By arithmetic, that will equate to 100 millimeters. So of course, note that we have here the distances of 31.25 and 37.5. So of course, we base our calculation on the gross yielding area. So we calculate the gross area, 31.25 plus 100 plus 37.5 multiplied by our thickness. So notice here that there will be no deductions from any of the bolt. So this is just a bare length times thickness, or the width of that member times the thickness. Again, we have 31.25, 100, and 37.5 multiplied by the thickness. And that will yield to 1054.69 square millimeters. Knowing that area, of course, we now apply the design strength, FYAG. So 248 times 1054.69. So we have 261,562.5 newtons. And that is equal to 261.56 kilonewtons. Now, remember that the allowable PN is given by the equation 0.6 of FYAG. So actually, these formulas will be under allowable strength design. So that the allowable PN is 60% of FYAG, that is equal to 156,937.5 Newton. And that is also equal to 156.94 kilonewtons. So the second unknown, of course, we need to consider some area or the net width. Okay, we are concerned with the net width or the least net width we can calculate from this staggered connection. Of course, primarily we consider the first row, okay, considering ABC. So the net width on ABC is 168.75. So that is actually the sum of these three. And then of course we'll just have to multiply that by or deduct 22. We should deduct this by 22. So this is equal to 146.75 millimeters. Now considering the other root, of course the root we'll have to consider now, DEBC. So on the root we have 2 bolts included. So the net width now is 168.75. Of course, we less the 222 millimeter diameter. And of course, there will be a pitch and a gauge distance here. So we apply the D prime formula. We have S squared all over 4G. So let us correct this equation. This is S squared all over 4G. So the pitch is 37.52 and the gauge distance G is 100. So with that, we can have the net width to be equal to 128.27 millimeters. Now between these two net widths, of course, we consider the least net width. So letter B, so the capacity of the section based on the tensile fracture of the net area. Of course, the capacity, so when we say capacity again, we refer to ASD method. So AN is equal to 128.27 or the least among the net width multiplied by the thickness 6.25 millimeters. So that would yield to 801.69 square millimeter. Now in your ASD, of course, we are familiar with this. For fracture, we have 0.5 FU times AE. Notice that the multiplier here should be AE, but in the problem, we consider the net area. So therefore, we do not need to multiply a reduction factor U to get the net area. We'll just have to stick with A sub n or the net area in this special case. So applying that formula, we have the tensile capacity is equal to 160,338 Newton, or that is equal to 160.34 kilonewton. So this is the answer for letter B. Next, letter C, determine the capacity of the section based on the block shear failure. Now, the first assumption here, or the first case, is actually projecting a shear block from the edge, of course, namely FEBG, that is enclosed. Okay, so that the shaded portion will be torn. Okay? So considering lines FE and BG, why lines FE and BG? Because lines FE and BG is parallel to the loading. And that parallel area is actually the shear area. While EB is actually the length perpendicular to our loading. Only that is inclined because of the staggered connection. Hence, note here that there will be a pitch and a gauge distance. Now, computing for the shear area first. So, the net shear area is equal to 150 minus 22 minus 11. So, this is actually calculating these blue lines here. Okay, 150 or 75 times 2 from F to E minus 22 minus half of the diameter that is located at E. Okay, this is the line actually. And of course, for line BG, of course, that is 187.5, or we have 5 times 37.5, that is 187.5 minus 22. There are two 22 diameter minus 11. So half of 22 again at the edge of B, the bolt B. So these are actually those lengths. So all we need is to multiply that by our thickness, 6.25. And this will be our net shear area, equal to 1,559.375 square millimeters. Now, for the tensile area is actually the line E to B. And that net tensile area is equal to 100, of course, minus 11. Why 11? The half of the bolt at E, and another 11 for the half dimension bolt at B. So this is actually the line for that one. Of course, we take into account the D prime formula, or S squared all over 4G. Now let us correct that expression. This is S squared all over 4G to account for the pitch distance. So again, we multiply that one by the thickness. Hence, we arrive at 509.47 square millimeters. Now, we apply the tensile formula for SI units. The first term is 0.3 FU net shear area. The second term is UBS times FU times the net tension area. Of course, applying the formula, we take note that we have here a staggered connection, and that is not uniform or non-uniform configuration. Hence, we multiply UBS of 0.5. So, applying the formula, just have to substitute the values. So, that tensile capacity will be equal to 289,019 newtons. Or that is 289.02 kilonewtons. That is for case 1. For case 2, in here, we have the projected shear block FEBC. So of course, the shaded portion here will be torn out from this tensile member. Now, this time, we have the line for FE as the shear area. Okay, FE is parallel to our loading, and the perpendicular inclined area is the tension area EBC. So first, for the line FE, the net shear area is equal to 150 minus 22 minus 11 by 6.25. So this is actually that line less the 22 and the half of the bolt diameter at E, that is 11. Hence, we can get the net shear area to be equal to 731.25 square millimeters. So moving on to the tensile area along line EBC. So on that line EBC, the net tension area is 37.5. That is from C to B. Okay, from C to B is 37.5 minus 11. Of course, we deduct the half of our dimension. Okay, so this is the line. And then of course, we also add 100 minus half of the bolt at B and the half of the bolt at E. And that is actually this distance. Okay. Accounting for our D prime, because we have a pitch and a gauge distance, we have S squared all over 4G. The pitch distance is 37.52 and the gauge distance is 100. So 37.52 squared all over 4G. So this is attributed to this inclined staggered connection here. So all of which will be multiplied by the thickness 6.25. So we get 675.1 square millimeters. And finally, we apply the formula for tensile capacity for SI units. Of course, there will be UBS here, wherein UBS is 0.5 given that we have a staggered connection. So applying the formula for the first term, we have 400 FU, 731.25 for the net shear area, plus 0.5 FU is 400, 675.1 for the net tension area. We have 222,770 Newton, and that is equal to 222.77 kilonewton. And that will be the answer. Okay, so what will be the capacity due to block shear? So a while ago, we have computed the tensile using case 1 with 289.02. This time, we have a lesser value of 222.77. Hence, we choose the least value. Therefore, case 2 prevails in this example. Hence, we use the tensile capacity of 222.77. Okay, so that's it for this session. Thank you, class, for listening. Have a good day.